Hello everyone and welcome back to the channel. In modern system design, data is rarely stored in just one place. It's replicated, sharded and distributed across multiple servers, often globally. But when you update data, how do you ensure that all these copies are in sync? This leads to one of the most fundamental and critical trade-off in distributed systems, which is consistency. Today we are diving into two main models, strong consistency versus eventual consistency, a topic that's absolutely vital to master for any system design interview. Okay? So the challenge arises because distributed systems face what's known as the cap theorem. What the cap theorem mean? We have three things. We have consistency. Oh, this is a bad circle. Let me delete this. We have consistency, we have availability, and we have partition tolerance. Okay? And it says that any system can only guarantee two of these three. Like you can guarantee consistency and availability, and you sacrifice partition tolerance. You can guarantee availability and partition tolerance and sacrifice consistency, or you can guarantee consistency and partition tolerance and you sacrifice availability. No. So again, this theorem states that distributed system can only provide two of these three guarantees: consistency, availability, and partition tolerance. And since partition tolerance or network failures or failures in communication between parts of your system are inevitable, and in real world distributed system you cannot afford that. You effectively have to choose between consistency and availability. This choice defines your data model. Okay, so right now we understand the challenge, why actually we have consistency versus eventual consistency, or strong consistency versus eventual consistency, because the cap theorem that states that we cannot actually guarantee all three guarantees at the same time. We have only to choose two, and since partition tolerance, it's we cannot avoid it, or it's inevitable. We have to choose between consistency and availability. Okay, so let's start talking about strong consistency. In strong consistency, we prioritize consistency over availability. So in strong consistency, if a write operation, like let's say that we have a client and we have the server and we have multiple DBs, DB1 and let's say DB2. And when the client sends a write, okay, so if a write operation, for example, an update to the database record, is acknowledged as successful, then all subsequent read operations, no matter which server they hit, are guaranteed to see the most recent written data. There is no delay. All replicas are immediately consistent. So when you send a write request to the server and the servers try to update a 1 DB, the thing that will happen between the DB acknowledged this write request as successful, it will replicate first this data to all the other DB services, and after that it will send a successful response that yeah, you have updated this successfully, and it will be sent back to the client. By replicating and everything in synchronous way, not asynchronous, in synchronous way, we make sure that our system is consistent and all nodes read the same data at the same time. Think of a single perfectly synchronized bank ledger. When you transfer money, every teller, every ATM, every online banking app instantly sees the exact same. Latest balance. There is never a moment where one part of the system has all data. So how it works again? You can use like something like consensus algorithm, and we will talk about that in the future. such as a Paxo or Raft, used in systems like Zookeeper or or etcd, where a majority of nodes must agree on a state before a write is committed. Also, there is a two-phase commit for distributed transactions, where all participating nodes must commit or roll back together. Also, there is asynchronous replication, and this is the example of asynchronous application. Synchronous replication writes are committed to multiple replicas synchronously before acknowledging success to the client. The pros of this one, it's we have data accuracy and predictability. Like, you always read latest data, simplifying application logic because you don't have to worry about stale reads at all. It's essential for critical operations, like non-negotiable for financial transactions, critical inventory management, or unique identifier generation. What is the problem actually with strong consistency? First, we have higher latency because writes take longer because they must wait for multiple replicas to confirm this write. Second, we reduced our availability under partition. To maintain consistency during a network partition, the system might have to halt writes or reads on one side of the partition, sacrificing availability. We here favoring a C and B in the CAP theorem. So our system here is CB. We are favoring consistency and partition tolerance. Okay. So what is eventual consistency? So in eventual consistency systems or eventual consistent systems, after a write operation is successful, the data will eventually become consistent across all replicas. However, there might be a delay during which different replicas could serve slightly different or stale versions of data, I guess. The system guarantees that if no more writes occur to the data item, all replicas will eventually converge to the same value. So again, if we have the client that try to send request to the server, and we have two DB instance, DB1 and okay, let me delete this. DB1 and DB2, and the server tried to update, make a write request to DB1. The DB2, once the write request is accepted in DB1, it will send acknowledgement that it's okay, this write is successful, and eventually or asynchronously it will update DB2. So imagine updates as spreading through a rumor mill or social media feed. If you post something, your friends will eventually see it, but there is a lag. Some friends might see it instantly, others after a few seconds or minutes, depending on their network location. So how it works with asynchronous replication. As I talked, we call this asynchronous replication. Writes are acknowledged quickly to the client after being committed to local replica. Replication to the other replicas happen in the background. Also, we have a conflict resolutions like mechanisms like last write wins, where the most recent update is kept, or more complex strategies like vector clocks are used to merge divergent data if multiple concurrent tries occur before replication completes. The pros of this strategy, it has a lower latency. As you can see, we didn't wait to replicate data to all servers. We just acknowledged it right away. So writes are very fast, improving responsiveness. Number two, higher availability. The system remains available for reads and writes even during network partitions or node failures. Also, we have a massive scalability, like easier to scale horizontally across many geographically distributed nodes. But what are the problem with this system? First, we have stale reads. Like, applications must be designed to gracefully handle the possibility of reading outdated data. Number two, complexity in application logic. Like, developers need to consider the implementations, like user updates their profile and then immediately reads their old profile data, things like that. Also, we have a conflict resolution, like requires a careful design of how to merge data when multiple divergent writes occur. Okay, So when to choose which? I would say you choose strong consistency when data accuracy and immediate consistency are paramount, and you can tolerate higher latency or potential temporary unavailability during partitions. Use cases for that, I guess it will be financial transactions, critical inventory counts, unique ID generation. You could choose eventual consistency when high availability, low latency, and massive scalability are more important than immediate consistency, and your application can tolerate some staleness in reads. Use cases for that like social media feeds, e-commerce product catalogs, user profile, IoT sensors, data, online gaming, leaderboards, and etc. So, how to discuss it in system design reviews? In system design reviews, define both models clearly. Then crucially allows always discuss the trade-offs. Justify your choice based on the specific requirements of the use case of your system. Like for example, for our payment processing, we require strong consistency to prevent double charges, even if it adds milliseconds of latency. However, for the user activity feed, for example, eventual consistency is acceptable to ensure high availability and scalability. You need to show an understanding of how eventual consistency impacts your application logic and how high consistency or strong consistency will affect your application logic as well. So that's it for this video, and see you in the future.